Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this video on iterative eigenvalue methods. So what's motivating us here? Well, hopefully by now you're quite frustrated and sick of calculating characteristic polynomials. It's not because eigenvalues and eigenvectors aren't awesome. Let's face it, they really are awesome. But calculating the characteristic polynomial can take a long time. It's okay for a 2x2 matrix, but even for a 3x3 matrix, which isn't really that big of a matrix, it just takes such a long time. You have to calculate the characteristic polynomial, then solve it for the eigenvalues, and then do each one separately and find its associated eigenvector. Imagine if you needed to do that for a 100x100 matrix, which some people in the real world need to do. They need to find eigenvalues and eigenvectors for really large matrices. Of course, you wouldn't calculate the characteristic polynomial by hand for such a large matrix, but even getting a computer to calculate it is really difficult because it requires so many operations. So we need other methods to calculate eigenvalues and eigenvectors. So iterative means it uses iteration, which is basically a repetitive mathematical operation. So you'll see what we're going to do is start with a guess for an eigenvector and repeatedly apply a matrix to that vector. And originally, we should get a good estimate for an eigenvector. So there are two methods I'm going to go through in this video. They are essentially the same method, but I'll explain the difference. So the first method is called the power method. So let's look at why this works. So firstly, it requires our original matrix A to be non-defective. So we went through what a defective matrix was in the previous lesson. I should point out that the power method sometimes works on defective matrices, but we can't be sure that it will work. So what is it about defective matrices that makes them desirable for this method? So the property that's really desirable for non-defective matrices is that if A is an n by n matrix, it will have n linearly independent eigenvectors, and that means those eigenvectors will span Rn. What that means is that if I take a random vector q in Rn, I can write it as a linear combination of the eigenvectors of A, something times x1 plus something times x2, all the way up to something times xn, where x1, x2, and so on are the eigenvectors of A. So if the vector q is non-zero, then what that means is that at least one, usually quite a few, of these weights C1, C2, all the way up to Cn will be non-zero. So for each of these weights Ci that is not zero, it means that Q sort of points in roughly the same direction as the eigenvector Xi. So if C1 is not equal to 0, that would mean that Q, to a degree, points in the same direction as X1. There is some component of Q that is in the same direction of X1. So you probably realize it doesn't matter the way I order these eigenvectors x1, x2, x3, all the way up to xn. So what I'm going to do is I'm going to order it so x1 is the dominant eigenvector. So the dominant eigenvector means that x1 has the largest associated eigenvalue. So if its associated eigenvalue is lambda 1, its absolute value is greater than or equal to the absolute value of any of the other eigenvalues of A. So it's important to note this because the power method usually converges to the dominant eigenvalue eigenvector of A. It actually depends on your original guess. If you just so happen to start by picking a matrix Q that is very close to one of the actual eigenvectors, it might converge to that eigenvector rather than the dominant eigenvector. But in general, what happens is if you start with the matrix Q and you repeatedly apply to it the matrix A, we can write this a little more conveniently. So if I apply A to Q, I get another vector. If I apply A to that new vector, that's the same as writing A squared Q. That gives me another vector. And if I apply A again to that new vector, I get A to the power of 3 times Q, and so on. So if I apply this K times, apply A K times to my original vector Q, I have A to the power of K times Q. I know we haven't gone through matrix powers here, but we don't need to have gone through that. We're just taking A, applying it to a vector, getting another vector, applying or multiplying A by it again. Then we get a new vector, we multiply A by that new vector, and so on. So it turns out that this will converge to some scalar multiple of the eigenvalue to the power of k times the eigenvector. As I said, the eigenvector to which it usually converges is the dominant eigenvector. But depending on your initial guess, sometimes it could converge to another eigenvector if your original guess was close to one of the non-dominant eigenvectors. So the rate of convergence is given by the ratio of lambda 2 to lambda 1. Lambda 2 is the second dominant eigenvalue, or if you like, the eigenvalue that has the second largest absolute value. So the power method converges much faster when the dominant eigenvalue is much, much larger than the second dominant eigenvalue. But if the two most dominant, the two eigenvalues with the largest absolute value are close together, the convergence is much more slow. So I hope I haven't complicated this too much because I wanted to try and explain why it works. But really the method is simple. You just start with your matrix, start with an original guess of a vector, and keep applying that matrix to the vector until you get an eigenvector. So let's look at an example. So let's look at the power method in action with our matrix here A and our original guess for an eigenvector Q0. Remember, your original guess can never be the zero vector. So my first iterative guess, I'm just going to multiply A by the original vector, and if I do that, I get the vector for 2. Now remember, if x is an eigenvector of A, then so too is any non-zero scalar multiple of x. So why am I telling you this? Well, there's nothing in the power method that will prevent matrices like this getting arbitrarily large or arbitrarily small. In computational terms, we need to protect against overflow and underflow errors. So what we can do to stop these matrices getting really large is we can take out a factor of the largest entry in the vector. So 4 divided by 4 is 1, 2 divided by 4 is 0.5. This will stop the matrix getting too large. Of course, we need to think twice if there is a huge difference between, say, the first and second entries here. If the first entry was way larger than the second entry, for example, dividing by it will make this entry close to 0. But that isn't a problem here. We just need to find a scalar multiple of the vector that is less likely to get really large, small. So our second iteration, I'm just going to apply the matrix A to the vector Q1. Instead of applying it to this vector, I'm going to apply it to this vector, which I can do. There's no problem with that. It'll just stop my new vector being really large. So if I multiply them together, I get the vector 1.5, 0.5. Again, I'm just going to take out a factor of the largest entry in the vector. So I get this, okay? So what I can do is keep applying A over and over again. So if I do this, eventually I end up with Q9. On the 9th iteration, I end up with this vector here, 2.005 times this vector. And then if I apply A to this vector, I get Q10 equals about 1.998. I have this here. So what hopefully we can see is that the number in front here is approaching 2, and this vector here is getting closer and closer to the vector 1, 0.4. So it turns out that 2 actually is an eigenvalue of A, and this actually is an eigenvector of A. So here, the power method has converged. It's getting closer and closer to an eigenvalue and an eigenvector. So here it took a lot of iterations because it turns out the other eigenvalue is -1, which is sort of close to 2. It would have got there a lot faster if, say, the dominant eigenvalue was 2 and the other eigenvalue was like 0.2, okay? This method has worked after a certain number of iterations, and of course for a 2x2 matrix it would be easier to use the characteristic polynomial, but I want us to practice by hand using this on smaller matrices, because when you get to larger matrices you can't use the characteristic polynomial. So now we're going to look at the inverse power method. What is the inverse method all about? Well, if we have our matrix A, it turns out we can construct this matrix B. It's A minus alpha I inverse. Now, I know we haven't actually done inverses yet, but you don't actually need to calculate B and actually construct it in order to use this method. So it can be shown that if lambda is an eigenvalue of A, then the eigenvalue associated with it in B is 1 over lambda minus this number here, alpha. So that's the eigenvalue for B, and it turns out that both of these have the exact same eigenvector. But again, you don't actually need to construct B in order to use the inverse power method. So the inverse power method, the steps are more complicated. To actually do the calculations will take longer than the normal power method. However, the convergence is usually really quick. Another benefit of the inverse power method is whereas the power method almost always converges to the dominant eigenvalue and eigenvector, it turns out that the inverse power method can converge to any eigenvalue we want. We just need a decent sort of approximation for it. So what's all this stuff here about alpha? Well, alpha is an estimate that we have for the eigenvalue that we're interested in. And again, we can be interested in any eigenvalue of the matrix. The largest one, the smallest one, whatever. So we follow these steps here. We start with an initial vector. We have to solve an equation. Then we calculate the estimate for the eigenvalue. And then we repeat the iterative process, okay? So please pause and copy down these steps if you need. I don't have enough room to do the actual method and show you an example with all that writing here, and you might need to refer to it in my example. I'm going to perform a few iterations of the inverse power method on this matrix here, A. So I'm just going to guess that an eigenvalue is 4. It doesn't really matter whether I know whether that eigenvalue is the largest eigenvalue or the smallest or whatever. So in practical situations, you usually have sort of some idea of what the eigenvalue will be. So this method will converge to the eigenvalue closest to 4, and it will also give its associated eigenvector. So I'm going to choose my initial guess for the eigenvector as 1, 1. Remember, I want the largest entry of my original guess to be 1. That just stops the vectors getting arbitrarily large. So, following the steps on the previous slide, I first calculate A minus alpha I. So A minus 4i, I'm going to use this matrix quite a bit. So I just subtract 4 from the leading diagonals and I leave the others alone. So now what I'm going to do is I'm going to solve a minus 4I times some vector y0 is equal to x0, which was my original guess. So I set up my augmented matrix and row reduce it. At this point, you've probably had enough practice for row reduction. It's okay if you want to use like an online calculator. So this is the matrix I get in row reduced echelon form. So that means that my vector y is minus 1 2/3. So the next step, I needed to find mu 0. That's just the entry of the vector y with the largest absolute value. So my guess for the eigenvalue is my original guess plus 1 over mu 0, which is just 3. So that's my first guess for the eigenvalue. So then my next guess for the iteration, which I call x1, so the original guessing's done, that's going to be 1 over mu k, which is minus 1, multiplied by the vector y0. And of course, that just gives me 1 and minus 2/3. So please pause and copy this down because I'm going to get rid of it and then I'm going to do the next iteration. So I found out that my guess here, x1, was the vector 1 minus 2/3. So I follow the process again. I need to solve a minus 4I times some vector, this is now going to be called y1, is equal to x1, this vector here. So again, I set up my augmented matrix. This is a minus 4I, and then I put in the entries of x and row reduce that matrix. So that's the row reduced matrix I get, and of course that means that y1 is minus 2 2/3, and then 2 1/3. So again, I calculate mu 1 in this case, so that's easy. That's just the entry of y with the largest absolute value. So my estimate for the eigenvalue here is my original guess plus 1 over mu 1, which gives me about 3.625. I shouldn't use approximate. It's exactly equal to 3.625. So now I'm ready to start the next iteration. So my next guess for the eigenvector, that will be 1 over mu 1 times by the vector y1. And if you put that through, you get the vector 1 and minus 0.875. So hopefully you can see the fact that our original vector x0, its largest value is 1, means that in each subsequent vector, the largest value is always 1. So that's my x2 value. So again, I'm going to get rid of what's on the screen. Please pause and copy it down if you need. So I'm going to do one more iteration to get even closer to the eigenvector and eigenvalue. It turns out we're actually very close as it is. So now I need to calculate y2, so I need to solve a minus 4I times my vector y2 is equal to this vector here. So once again, I set up my augmented matrix. So I perform the usual row reduction and I get my vector here, y equals minus 2.875 and 2.5416 recurring. Okay, so again, I need to calculate mu2 in this case, so it's just the entry in y that has the largest absolute value. So it turns out here, my estimate for the eigenvalue is 4 plus 1 over mu 2, which is about 3.6522. And then I can calculate x3 here. I won't do another iteration after this. So remember, that's just 1 over mu 2 times y2. And that gives me the vector 1 minus 0.8841. So I'm going to stop there. Turns out for matrix A, the eigenvalue that's closest to 4 is about 3.65331, obviously to 5 decimal places, and the associated eigenvector is 1 minus 0.8844. Okay. So remember, of course, any scalar multiple of this will be an eigenvector. Look how close I am. This is so close to the eigenvector. It's minus 0.8841 instead of minus 0.8844. And of course, my guess for the eigenvector is pretty good too. 3.6522 instead of 3.6533. So you might be thinking, okay, this was a little bit tedious to do by hand. But let's think of what we actually did. At each step, we were solving an equation, and then when we got our solution, we just calculated the entry in the vector y with the largest absolute value. And then finally, we got an estimate from the eigenvalue, which was a simple subtraction. So all of those things that I just described at each step, though they can be tedious by hand, well, really, the solving of a system of linear equations by hand, that was the thing that took the time. But all of those things can be done by a computer quite quickly. And it only took a few iterations of this method to get really close to the actual eigenvalue and actual eigenvector. So that's why this method is so powerful. Performing, heaps of iterations of this method is computationally so much less expensive than calculating the determinant, which we need to come up with a characteristic polynomial and then solve that polynomial. So that's why these iterative methods are so important. Yes, particularly the inverse power method may take quite a bit of effort by hand, but it's a lot less effort for a computer. All right, I'm sorry again for the long video. I hope you've enjoyed it. This has been the luckiest maths teacher in the world. Have a great day.